is the exam. So will Friday morning be okay? Like if I hand out the PDF say at 11 and ask you to submit by 1:30 or something like that. So I mean Saturday, I mean. So Saturday, which is 31st. Right, as I said previously, the end of every month I will be taking these exams. So this is October end. So 31st Saturday, if I give you the exam and ask you to scan and send them back, I'll have to actually figure out how to do it on Teams. There's a way to do it, but I think we'll figure it out before Saturday. Does that sound okay?
Yes, sir. It's better if it's in the morning. I mean, at around 11.
Yeah. So 10:30, 11 is what I was thinking. So that you're, the exam is 2 hours and a half an hour extra is given just for you to submit. Okay. Okay, then if that is fine, let's sort of reserve Saturday for the exam. So the exam will be like, I will be putting a PDF and you guys will have to solve them within 2 hours and submit it within 2.5 hours. And the exam will have like 1/4 the weightage of the total course. And it will be based on the material that we have covered till now. So homework 1, as I said, I will give a lot of questions from homeworks itself. So it's a good idea to work out the homework. Okay. So we are actually done with chapter 1, the relevant portion of chapter 1 of the book. Now, so that was really a simple radiative transfer theory, and just simple picture of how radiation interacts with matter, black body, Planck spectrum, and so on. Now we will actually go to basically electromagnetic theory, advanced electromagnetic theory as it is relevant for, classical treatment of radiation. Okay, so we are sort of starting with chapter 2 of the book. So I would actually encourage you to review your electromagnetism courses, specifically time-dependent Maxwell's equations. In the end, we will actually go to electromagnetic radiation, right? So it's sort of this is the portion which is covered like at the end of electromagnetic theory courses, whereas here we will encounter it right away. So I'm assuming that everyone has done E&M and knows Maxwell's equations and concepts like electromagnetic waves, although we will review them a little bit. Is there anyone here who has not done electromagnetism, any course on electromagnetism? No, good. So everyone knows, some electromagnetic theory, at least basic E&M at the level of Griffiths. Good. So let's get started. So this is, as I said, chapter 2 in the book. So any questions, by the way, before we move on to the next portion? So we will actually meet on Friday as usual with the TA. And if you have any doubts and so on, you can come for that session. So let me get started with the lecture today. So the course is pretty well divided into modules. So the first module is over, and you can also see the syllabus, how these modules are. Okay, so let me share screen. Okay, so so this is basically you know, this is about, you know, basics. Just a sec.
Sir, just one quick question. This
Yeah.
is Kinjal. The syllabus is only chapter 1, right?
Yes, yes. The
Okay.
syllabus is only till the last class,
Okay.
which we did, which is the whole of chapter 1. I may add a few questions in homework 1, just so that, you know, you have some
Understood.
more practice. But I will actually mention that on the on Teams. So yeah. So right. So only chapter 1. Today, what I'm teaching today will not be in the exam. Okay. Basics of radiation fields. Basically, this is the classical treatment, right, where we don't really bother so much about the quantum nature of photons, but treat it as an electromagnetic field, right? So, you know, so these are the equations, and this stuff is very, very familiar to everyone, and it's a good idea to, you know, get back to it a little bit if you're not so familiar with it. So, you know, let me first start with the Lorentz force. Okay, so Lorentz force, right? Lorentz force is the force acting on a charge q, right, in presence of electric and magnetic fields. Electric field vector is given by E, and magnetic field vector is given by B. And again, we are using CGS units. So E and B have the same units in CGS. So this is Lorentz force. So this is the electromagnetic force felt by a particle of charge q moving in this electromagnetic field given by E and B with velocity v. Okay. So, right, so if this is the force, we can write the equation of motion as dp dt is equal to the Lorentz force. Right, so this is Newton's law. And we will actually be dealing with relativistic particles. So I also encourage you to revise some of special relativity. So things like P is equal to gamma mv, where gamma is this relativistic gamma, which is 1 over 1 minus beta squared, and v is the velocity particle velocity. So I am assuming that everyone has done some relativity beforehand. Is there anyone in the class who does not know this formula that I have written? Okay, so good. So everyone has seen some relativity. So basically, relativity is the generalization of classical mechanics when the velocity approaches the speed of light. When velocity of particles of matter becomes close to speed of light, you have to be very, very careful because space and time that we are used to thinking in Newtonian mechanics get coupled, and there are a lot of interesting and non-intuitive effects. Okay, so this is basically special relativity, right? And special relativistic effects become important when V becomes of order, when V approaches C. And this is actually very common in a lot of astrophysical scenarios that we are considering. So later on, we'll deal with synchrotron radiation and inverse Compton radiation, and we will need concepts from special relativity. So I encourage you to actually go back and read up a little bit if you're not that familiar with the concepts. Things like Lorentz transformations and four vectors, little bit of how the electromagnetic field is represented in in relativistically covariant formalism. If you can read up all that, that will be very useful to you. Okay, so yeah, so that was just a digression. So so special relativity and all, a lot of this material actually is covered in Griffith's book, but not so much special relativity. So for this, you can read whatever is your favorite book, or wherever you studied it as an undergraduate. Okay. So right. So this is the equation of motion. So and so beta is equal to, so the beta is this velocity by c. Okay. So basically in relativity says that nothing can be accelerated to speed of light, and speed of light remains the same whatever frame you look from, right? So if you have a light ray traveling, and if you're traveling towards it in your frame or in some other frame, it always travels at c. So all this is a result of Lorentz transformations. In fact, Lorentz transformations are constructed to ensure that speed of light is the same in all frames. Okay, so please brush up these concepts, because we'll be increasingly using them later on in this course. Okay, so let's get back to our Newton's law. So the equation of motion is gamma mb equals q e plus v cross b by c. Okay, now and we also know that energy of a particle is equal to gamma mc squared, right? And which is equal to p squared c squared plus m squared c to the 4 for a particle with rest mass m. So here, okay. So right, so this is the equation. P is this magnitude of momentum, m is the rest mass of particle, gamma relativistic factor. So all these things are defined. So again, I'm not sort of saying much about these. Okay, so now and E is equal to this. This is the energy. This includes both the rest mass energy and the kinetic energy. Okay, so if we do V dot of this, right? So this is the equation of motion. So if we do a V dot of equation of motion, we get an energy equation. Right? So just notice this E and this E are different. This is electric field, and this is energy. Okay, so so this actually ddt. This is again energy. This is equal to mc squared ddt of gamma is equal to, if F is the force, so this is F dot V is the work done by the external force, right? Now from here to here, you can actually show this. I will not prove it. you can actually show that v dot d dt of gamma mv can be written as this, right? Here you have to recall that v gamma equals 1 over 1 minus v squared by c squared, right? So when you take this time derivative, you also have to take the derivative of gamma, and if you do all the algebra right, you get this. So I'll not do this, but it's not that hard to show. In fact, I have perhaps given this as a homework problem. So this is the energy equation. So the rate of change of energy of the particle is equal to the force dot v. And if we have Lorentz forces, if electric and magnetic forces are acting, it is just equal to q E dot v, right? The magnetic force is always perpendicular to v because it's v cross b, proportional to v cross b. So v dot v cross b is 0. Okay, so in other words, magnetic forces don't work on particles. They don't increase the energy of the particles. They don't do any work on particles because the magnetic force is always perpendicular to velocity, instantaneous velocity of the particle. Okay, so this is the change in energy of a particle. This is work done due to external forces. So this is good. So this is like a sort of work energy equation in some way, right? So this is the work done, and this is the change in energy. This is work done per unit time, or more like power. Okay, good. Now, so we'll actually come back to this, but let's go to let's sort of review Maxwell's equations. Right. So Maxwell's equations are the dynamical equations for E and B. How do E and B evolve in time is governed by Maxwell's equation. So this equation governs how charges move given E and B, right? E and B are fields. These are vector fields which depend on position and time, right? Now, once these are specified, you can actually solve particles' trajectories and see how they move. But how do E and B themselves evolve is given by Maxwell's equations, which are, so I'll write the Maxwell's equations here again in CGS unit. So del dot D equals 4 pi rho. Let me just write it down and then I will mention what all of these are. So these are the divergences, so del, and now these are the curls, del cross del cross E is equal to minus 1 by C dou B dou T, and the del cross H equals 4 pi by C J plus 1 by C dou by dou T of D. Okay, so I've introduced some new fields here. So let me actually finish. So D equals epsilon E. This is called the displacement field, and it's related to the electric field by this permittivity tensor, okay, or dielectric tensor. And similarly, B, magnetic induction or magnetic field, is equal to mu times H, right? So this epsilon and mu are used to sort of take, to include matter response, right? Okay, so so question. So all of you have seen these equations, Maxwell's equations?
Yes, sir.
Good. This D is the displacement field. H is also related to B. Right. So here, these are the sources of fields, charges and current, charge and current densities, right? And these are free charge and current density, right? So basically here, there is this whole formalism that we do where, so for example, in case of electrostatics, right? If we put a dielectric in between capacitor plates, the dielectric, there are charges induced on in the dielectric. So the charge we put on the capacitor plate is affected due to the charge induced in the dielectric. So that response of the material is taken care by constructing this D. And this is where the dielectric constant goes, right? But this rho and J are free charges and free currents. Okay. You can also, you can actually also include those polarization charges and induced currents on the right hand side. Okay, there are two ways of looking at the same thing. So this is just a review of little bit of electrostatics and and magnetostatics. Okay. Okay, and in CGS units, epsilon and mu are actually 1. So this is why there is no 4 pi epsilon naught and mu naught by 4 pi hanging out. So it's actually nice. CGS units are actually better in terms of the equations being more, less messy. Okay. So E equals mu equals 1 in vacuum. But this is non-zero if you have a medium where charges and currents can be induced. So, for example, in presence of dielectric material or in presence of magnetic materials which can be magnetized, and an external magnetic field can induce dipoles in them, then mu will not be 1. But we will actually not be dealing with this. We'll actually mostly be dealing with vacuum conditions. Okay, so let's see how much E&M do you know. What is this equation? This divergence B equal to 0. What is this equation called? Or what is the implication of this equation?
Magnetic monopole don't exist.
Yes. And who was that? Kinjal. Huh?
Kinjal, yeah.
Okay, so so this is the differential form of this equation, or we can actually also write all these equations in their integral forms, right? If we do a volume integral of this, so we get, and using Gauss's law, we get B dot ds is equal to 0 for any surface that we consider. So basically, if you have any surface that you consider, and if you sort of calculate B dot ds of over any surface, you should always find 0. That means you cannot have situation like in the case of electric charges, right? You have electric charges, and you will have electric field going out from a positive charge in all directions. So E dot ds is not 0 around the charge. So there are no such things as magnetic charges. So there are no magnetic monopoles. This is the interpretation of this equation. Okay, let's see. Someone else answer. What is this? So this one is no magnetic monopoles. What about the third equation, this one? What is the interpretation of this equation? Someone else. A lot of our daily lives is governed by this
If
equation.
if the
Yes.
magnetic field changes with time, then an associated electric field is generated.
Right. Who is that? Who?
Aratrika.
Aratrika. Okay. So what did you say? If the magnetic field changes with time, there is an electric field which is induced. Right. So this is Faraday's law. A lot of our, lives are affected by this. All dynamos, motors, fans, mixies are sort of fundamentally based on this. Okay. All the power that we receive is the magic of this equation. So EMF, this electric field is also called EMF, electromotive force, because it moves. Electric field moves charges and creates currents. So this is Faraday's law, that you can create EMF by changing magnetic fields across some loop. So the integral form of this equation, right? So it's E dot dl is equal to, so if you consider any closed loop, is equal to -1 by c d dt of phi magnetic. So phi b is nothing but b dot ds over this area. See, this b dot ds is not the same as this b dot ds. This is also looks like b dot ds. This also looks like b dot ds. Can someone tell me what's the difference? This is 0, but this is not 0. Why is that? Can someone tell me? These are both area integrals, but there is a circle missing in this integral. Can someone tell me why?
Green's theorem. I mean,
Yes. Yes, Kinjal, go ahead.
yeah. I mean, we are. I mean, I could not understand the question properly. Can you please repeat?
Right. So, what I did here, so this is del cross E equals -1 by C dou B dou T.
Yeah.
Now I'm writing this integral form of the same equation. Okay.
Oh,
I consider a loop and I
yeah.
do
That's
so,
the Green's theorem, correct? I mean, Green's
yes.
theorem we use for converting line integral to surface integral. So, I mean, it's just that, I mean, dl is the border of the surface. So we can
Yes.
choose surface with that border.
Right. So this is not a closed surface, basically.
Yeah.
That's why this is not equal to 0.
Yes.
Right? Because we are not considering a closed surface. Here we had a closed surface. Here we have a closed loop. Right? We only have a line which is closed. But this surface is not closed. It's not like a sphere or something, shell. Okay. So this is this is Faraday's law. Okay, someone else now tell me about this equation. This one. So, okay, so before that, do you know what was the contribution of Maxwell to these equations? Why are these, these equations are called Maxwell's equations? Not because all of them were sort of discovered by Maxwell. Maxwell introduced one term which is very, very important. Can someone tell me about that?
So it is a
Yes, sir.
displacement.
Displacement, fourth number equation.
This term was introduced by Maxwell. Okay.
Yes.
Okay, now let me actually ignore this term for now. Tell me the interpretation of this portion, the remaining part. What is the interpretation of this portion of equations?
So this is Ampere's circuital law. Means
Yes,
if we
this
have
is
a current carrying conductor and we have to find the magnetic field.
right. So what it means is that if you have a current anywhere, right, it introduces it creates magnetic fields. So if this is the current passing through this wire, then around this wire there will be magnetic field created. So the integral forms are much better for these differential equations. We do B dot dl equals 4 pi by c times j dot ds. So this is the current piercing this loop. So this is nothing but I, because J is the current density, current per unit area per unit, charge per unit area per unit time. So this is, if you multiply it by area, you get the current. Okay, so this is Ampere's law. How Ampere's law is very, very applicable. So with some magnetic fields, find the magnetic field due to this dipole configuration of current. Basically Biot-Savart law, right, is one and the same thing as this in a sense, right? Biot-Savart law says that if you have this current density, how do you get magnetic field strength? In the same way, right? So this equation, right, gives us electric field is equal to Q by R square R hat, due to a point charge, right? So this equation is sort of equivalent to this equation in the same way that Biot-Savart law is similar to Ampere's law. These are different ways of looking at the same thing, but the field description is more powerful. Okay, so this is fine. Okay, so what is the problem if we don't have the displacement term in the last equation that we have here? This term. Can someone speak up and tell? So this is.
Yes, sir.
Yes. Please tell your name and then speak up. Yeah.
I am Sipra.
Okay.
And if only we do the Ampere's law, then it shows that the density remains constant with the time. But if we consider,
how do we see that?
From the equation of continuity.
So tell me what I should do. Tell me what I should do with this equation so that I see that charge conservation is in danger.
Yes, if we take the divergence on both the sides of Ampere's law, then we get the divergence of curl of the magnetic field becomes 0. So that the divergence of J vector equal to 0.
Right.
From the equation of continuity, we know that dou rho by dou t plus divergence of J equal to 0. That is why dou rho by dou t equal to 0. That means rho becomes constant.
That's correct. So del dot J, basically if you don't have this term, del dot J is equal to 0. And that's not true in general, right? If you have time dependent charges, then this term has to be included. So this was Maxwell's contribution. Okay. Good. So I'm happy most of you sort of know the physical interpretation. So, in terms of the practical applications, Faraday's law is really, really everywhere. Faraday sort of made this sort of theory into something which is extremely practically important. All the motors, all dynamos, all power generation by moving turbines, by water or wind or whatever is based on this. Okay, good. Now let's get back to where we were. Oops, just a sec. So I'll create a little more space on this page. Okay. Okay. So this is all. So right. So right. So we wrote down this expression for the Lorentz force for a single charge Q. Now, if you want to consider force per unit volume, we can actually write it as rho E plus J cross B by C, right? So the Lorentz force, let me rewrite it, was QE plus V cross B by C, right? Now what I'm actually doing is the following. I'm saying let's consider a volume element, a small volume element delta V, okay, and it has some charges and protons and electrons, or positive and negative charges, and they are sort of moving in general directions. Okay, so if I calculate the force acting on this whole volume, what do I have to do? I have to sum up all these forces acting on individual charges. If I do that, so the force on this volume is nothing but summation over all these Lorentz forces acting on these particles, right? And that's nothing but summation over QI EI plus VI by C cross BI. Okay, so right. So if we assume this volume delta V to be infinitesimally small, basically like in hydrodynamics, in fluid dynamics, right? We can make in certain cases this assumption that this volume element is small compared to the macroscopic size of the system. In that case, these electric fields, and only in that case, and magnetic fields, which are only functions of positions and time, will not depend on the particle position, because this is infinitesimally small. So in that case, what you have is summation Qi times E at that location plus summation Qi Vi over all particles divided by C cross B. Okay. And this is the total force, and we just sort of divide it by this volume of this fluid element delta V. So this is 1 by delta V, and this is 1 by delta V. Okay, so this is nothing but charge density, right? This is nothing but rho, the charge per unit volume in this small volume, and this is nothing but the current density, right? So charge per unit volume per unit time, charge per unit area per unit time, right? Because velocity is centimeter per second, so this is basically charge crossing per unit area per unit time. This is the current density. So that's why you get an expression for force. So this is written as J, current density. So that's why you have force per unit volume given by rho E plus J cross B by C. Okay, but remember, we have made this approximation that within this small volume there are many charges, and electric field can be taken as constant over this volume. And this is a good approximation in a lot of cases, but not always. Okay, but for all the situations that we will be dealing with, we will, this will be fine. Okay. Now, what about the rate of work done? So, just a second. This is force per unit volume. Now, so this is force unit volume. So we do right. So if we want to calculate the work done by the electric field on each of these particles, so we should do Vi dot Fi. 1 by volume. So this is the rate of work done per unit volume in this on this system of particles. So so again, if I do Vi dot Vi cross B, that the magnetic contribution goes to 0. All I have is 1 by delta V summation over Qi Vi dot E. Okay, so this is the work done. So basically what I get is d dt of my mechanical energy density is equal to J dot E. Okay, so let me explain what I have written. So this is the work done by electric field on this ensemble of charges per unit volume. Work done per unit volume per unit time. So this is like power injected in some sense. Injected by electromagnetic fields in this volume. And where does this power go? This power goes in increasing the kinetic energy of the particles. If we go up and see the single particle form of this equation, this is the change in kinetic energy, or the change in total energy, mechanical energy of the system of a single particle is QE dot V. When we sum it over a small volume, we get this as a change in mechanical energy density. So this is mechanical energy density. And this is the work done by electric field. Work done by. Okay, good. Right. Right. So the other actually equation. So sorry, this is actually a little mess. So let me point it out. Just let me mark it by red. These are actually important equations. So then they're actually clear. Okay, so these are the Maxwell's equations, but we can actually supplement this with the charge conservation equation, dou rho dou T plus del dot J is equal to 0. Right, so this is this is just obtained by taking divergence of the fourth equation here. So this is charge conservation. Okay, good. So yeah, I'll actually move to the next page because I can actually see the computer, this screen getting slower. So this is. Okay, so it's taking some time because now I cannot write. Nope. I don't know why this I'm not able to write on this. Okay, maybe I will be able to write now. Okay, so so come to the energy equation. Energy equation for EM fields. Okay, so let me also put the date. So October 28 or 2. Okay. So so let me actually write down the equation first, and then let me tell you how we get it. Okay, so dou t of 1/8 pi epsilon E squared plus V squared by mu. Plus del dot C by 4 pi E cross H is equal to minus J dot E. Okay, so this equation can actually be obtained by, let me actually just show how we can get this. So these are our Maxwell's equations, right? So we have terms like dou t of D. So if you do an E dot of this equation, you will get something like dou t of E squared, right? And you will have J dot E from here, and you will have E dot del cross B. I'm actually using H and B interchangeably. We are sort of taking epsilon and mu to be 1. So this will be E dot del cross B. Similarly, if we do a B dot of this equation, we get B dot del cross E, and we can actually use vector identities to get, so to sort of combine them and get it in this form. I'm actually not deriving it because this is sort of like a this is all of you have done it if you have done an E&M course. So this is right. So this is the energy density of AM fields, right? So energy per unit volume is given by this, and this is represented by U field. If you recall, I used U mech for the mechanical energy density of the particles. This is the energy density stored in fields. Okay, and this is S, or the Poynting vector, which is the flux of electromagnetic energy, like energy per unit area per unit time crossing some surface. So again, the integral forms are very, very powerful. I'll actually talk about them. And if you recall, this guy, this was nothing but minus ddt of U mech, right? So this is the rate of work done. So J dot E is the work done per unit time per unit volume on a collection of charges by the fields, and that is stored in the mechanical energy of the particles in terms of motion of these particles in that volume. So right, so this is a differential form, right? Whenever you have dou t and del dot and so on, these are differential equations, differential forms, but we can actually look at the integral form of the equation, which is very powerful. If you take a volume and if you integrate this equation over this whole volume, so we have d dt of integral of U field dV, right? So that's nothing but 1/8 pi epsilon E square plus B square by mu dV over this whole volume, right? Plus, dV times del dot or something, we can always use Gauss's law. So this is S dot dA, where dA is this area enclosing this volume. So if If you integrate over this whole volume, this is what you get, and this is nothing but d dt of u mech dv, right? So this equation is nothing but the rate of change. So this is not a partial derivative. It has become only a time derivative because we have integrated over the whole space over this volume. So this is d dt of u. Capital U is energy in the field, not energy density. Small u is energy density. So this is the volume integral plus u, mechanical energy of the particles, right, is equal to minus integral of s dot dA. So if you have this closed volume with charges and fields, okay, right, so there is energy stored in the mechanical motion of these particles and there is energy stored in the field, okay, and the sum of the two energies is conserved except for the fact that energy is leaking through this volume because of the Poynting flux. If it leaks, it may also come in, but the change in the total energy of this volume, which includes the energy stored in electromagnetic fields and in the motion of particles, the change of that energy is given by the energy only changes if there is Poynting flux or the flux of electromagnetic energy crossing this volume. We are assuming that particles are not crossing, particles are all confined. We don't allow for electrons to move out of this volume, but we are allowing the fields, E and B fields, to cross it. And this is what the flux is given by. So this is like a energy equation for a collection of particles and fields. Okay. Now here we have actually also included the material response in terms of these epsilons and mu's. So if you have done like macroscopic treatment of fields, you will see that the energy interpretation, whether the energy is stored in fields or whether it's stored in particles, there is an ambiguity, because you can actually say that this epsilon and mu actually represents energy stored in the polarization, in the induced charges and currents. So, but here we are actually putting it all in the field energy. So what's important to note is that this equation is valid. The interpretation can be sort of somewhat different if you think in terms of free charges and bound charges and so on. Okay, so this actually is done in the standard books on E&M, but again, as we'll not be dealing much with matter responses, so epsilon and mu will be taken as well. Okay, so what it means is that E and B fields carry energy, right? Because they have this energy density like thing associated with them. This is like energy conservation. Okay, so the fields, E and B fields, carry energy. What about momentum, right? So momentum. So if we recall our photon picture, the
Hello.
Yeah, sorry, I had a power cut for some reason. I'm in my office still. I thought it would not happen. And my UPS somehow didn't work. Can you hear me? Hello?
Yes, sir.
Yes,
Yes, sir.
sir.
Now,
Good, so let's get back to where we were. I will start sharing. Oh, that was really bad. I didn't expect this to happen. So let me just start sharing again. Okay, so we were here. So we recall in the photon picture, we recall that the photon momentum is actually not able to type right. Just a sec. Let me see if I can type or write or something. Okay. Okay, good. We are back in business. Okay. So I think the computer just shut down, so that's why everything needs to be started again. Okay, so let me undo this and go back to drawing. So P equals E by C, right? The photon momentum and photon energy are related this way. Now the Poynting vector, right? The Poynting vector S is basically, if you consider this arrow, for example, if you have photons going from here, this is energy. So S is basically energy crossing this area, energy crossing per unit area per unit time. All right. So if we divide this by C, if we divide S by C, what do we get? We get momentum crossing this area per unit, per unit area per unit time. So we can actually define a momentum. So, in fact, momentum is a vector. So, and it sort of goes along the direction of the path of the photon. Actually, we are using omega hat, if you recall. Right. So we can actually define a momentum density in the field. So momentum density of the field G. So the field has energy, it has momentum, it has angular momentum, it has all these properties that we normally associate with matter, right? And of course we looked at the photon picture and we sort of know that we talked about radiation pressure, momentum, flux, and so on. So this is nothing but E cross B by 4 pi c. Actually, yeah. So this is the this is, if we just divide once by c, by c, what we have is energy crossing per unit area, or this is equal to momentum crossing per unit area per unit time, right? Because E by C is like momentum, so this is like momentum flux. But if we divide this further by C, so if we do S by C squared, which is equal to momentum, so if we have another C and at the bottom we have momentum per unit volume, which is nothing but momentum density. So we divide this expression in curly brackets by C squared, right? So first division by C gives us momentum flux. The second division by C gives us momentum density. Okay, so this is momentum stored per unit volume in the field, right? And similarly, you know, once we have momentum, right, we know that L equals R cross P, right? This is the angular momentum for a particle, and R is some, you know, relative to some coordinate origin. In the same way, as we have momentum density, we also can define angular momentum density, which is nothing but which is sort of, let's call it by curly L. This is nothing but R cross G. Okay, where G is given by this expression. So you see the fields not only have energy, they have momentum and they have angular momentum. So when we are applying conservation laws, for example, law of conservation of energy, law of conservation of momentum, law of conservation of angular momentum, and if you ignore the field, or if you're not careful about the fields, you will conclude wrongly that the total energy is not conserved or the total momentum is not conserved. So you have to actually account for electromagnetic contribution in all these conservation laws. Because photons or the fields conservation laws carry all these properties that we typically associate with just matter. Okay, I'm sure you've done all this in your E&M classes. If not, please brush up these concepts. These are all done in Griffiths as well, and also briefly in the book in Rybicki and Lightman. Okay, so let's look at this a little more closely. S dot dA, right? This term, this one, which represents how energy crosses just a second. Okay, which represents how energy crosses a volume. So let's say, you know, in electrostatics and magnetostatics, electrostatics and magnetostatics. So what is electrostatics? When charges, you know, rho and E, you know, we don't consider the time dependence, right? Similarly, magnetostatics, we don't consider time dependence in J and B. They're only functions of space. You know, the steady state conditions, like if you have a current carrying wire, how does B go as a function of distance? And similarly, if you're given charge distribution, how does E go as a function of position? These are problems of electrostatics and magnetostatics. We know that in electrostatics, if charge is all confined within some volume, then electric field at large radii goes like 1 over r squared in magnitude, right? If all the charge, you know, this is just dipole, this is the monopole contribution, and you know, and so on, right? Electric field goes like this. if your charge is all confined within a small volume. Similarly, magnetic field goes like 1 over r squared if all your currents are confined within a small volume. So your S, so you're considering a volume where all the charges and currents are confined, and you're looking at a so this is where all the sources are, sources of E and B. Basically, what are sources of E and B? Rho and J, right? So all the sources of E and B are in the small volume, and now we are considering this volume. So our Poynting flux S, which is like E cross B, goes like 1 by r to the 4th, right? And so S dot dA, and area goes like r squared. So S dot dA, the surface, so no, the surface integral over this area will go like, r to the minus 4 r squared, and this goes to 0 as r tends to infinity. Basically what it means is that in statics, when the charges and currents are not in motion, right, when the charges and currents are not in motion, and if you are looking at at an area which is much bigger than where the charges and currents are located, the Poynting flux sort of vanishes. Okay, so Poynting flux vanishes far from sources. This is only true for static situation, right? When we have time dependence, and in particular in something called radiation regime, right? In that case, E and B go like 1 over r, and your Poynting flux goes like 1 over r squared dA, right? If you do this integral, it is equal to constant. So basically, this is nothing but rate of this is energy crossing some area per unit time. This is like your right. So this is S dot dA. This is energy cross. So S is nothing but energy in EM fields per unit area per unit time. And if you multiply it by dA and integrate it over a shell, you get energy crossing per unit time. So this is nothing but energy crossing per unit time, some shell. Okay, and in this radiation regime, energy, the same energy crosses this shell or this shell, or sorry, what has happened? Just a sec. Okay, so the same energy crosses all these shells. So this is fundamentally different and much more interesting, right? We have electromagnetic radiation, photons coming from the sun, right? The sun satisfies this inverse square law that energy crossing any shell around the sun per unit time is a constant. Because we are in the radiation regime, all these charges which are dancing around in the sun, right? They are able to create this radiation field which decays like 1 over r and not like 1 over r square as in statics. And that's why you are able to transport energy to large just a sec, to large radii. Oops. Why am I not able to? Okay, good. We're able to transport. No, I don't want eraser. I want to. Energy to large distances. So that's why, you know, the radiation is really the most important, you know, one of the most important aspects of E&M. The ability for electric and magnetic fields to carry energy to large distances. This, you know, most of the energy is actually stored in this volume, and you know there's negligible amount crossing in statics. But when you have dynamic charges, accelerating charges, your E and B in the radiation regime fall very slowly, and that's why you can have propagation of energy to very large distances. In fact, you know, to infinity. Basically you can transfer energy produced here to large distances without dissipation. Okay, that's why we can observe things so far away, because you know this is electromagnetic radiation produced by these charges. Okay. Okay, so so it's 1:15. So I wanted to actually talk about electromagnetic waves in this class. So you have already done EM waves, right? Plain electromagnetic waves. Hello.
Yes, sir.
Yes, sir.
So how do you derive the wave equation? Do you know?
In vacuum?
Yes, in vacuum. Yeah, the simplest thing, right? The simplest thing. So
I think taking curl of.
I mean, yeah,
in
we
Maxwell equation.
set rho and j equal to 0, and then I mean, it's like using the properties we can get to that.
right. So why am I not able to? Why is the eraser appearing? No. So right, so what you do is you look at the solutions of Maxwell's equations in charge and current free locations. Okay, so what the heck? Mhm. Right, plane monochromatic. Monochromatic. Why am I not able to do it? Just a sec. No, I don't want this. Okay, looks like I will not be able to do it using this. Okay, anyway, we can actually end the class at this point, or we can actually talk a little bit. So you know, we will actually start with electromagnetic waves. You know that all of you have done, and then we will actually go to. We'll continue in the next class. Then we will actually, let me tell you what the sort of roadmap is. We'll start with plain electromagnetic waves. Then we'll talk about some Fourier, you know, the time and frequency representation of electromagnetic waves, some Fourier transforms and its properties. And then we'll actually go to polarization and the Stokes parameters and how to characterize polarized and unpolarized light using Stokes parameters. And then after all that, we will actually go to these electromagnetic potentials and retarded potentials. Basically how you generate fields, far fields, by charges and currents located in a small volume, which don't fall off like in electrostatics and magnetostatics. Right, so this is actually a lot of, this topic is very much like classical electromagnetism, but it's something that is not covered so deeply in the E&M courses. In a lot of E&M courses, we do electrostatics in great detail. We do magnetostatics in some detail, but not a lot of attention is paid to dynamic electric and magnetic fields and radiations and these retarded potentials. So I actually encourage you to read up a little bit on your own, so that the material is not that difficult to understand. Okay. Any questions? So we will have the exam on Saturday, and I will actually post more details on the Teams page, and we will meet on our usual office hour on Friday. So the TA will be there, Ankit will be there. Okay.
Okay.
Okay. Bye bye. Take care. Good luck.
Thank you, sir.